Hello and welcome. Today, we are diving deep into the world of organic chemistry. Now, I know what you might be thinking, but trust me, this is the fundamental code that literally writes the story of life itself. So, to get us started, let's kick things off with a little puzzle. What on earth could possibly connect something as hard as a diamond, the complex blueprint for every living thing, and the gas you put in your car? They seem about as different as you can get, right? Well, the answer comes down to one single, incredible element: carbon. Think of it as the ultimate architect, the master builder at the very heart of the millions of compounds that make up not just our world, but our own bodies. And that right there brings us to our main topic, organic chemistry. This isn't just some class you have to take, it's the actual study of these carbon-based molecules. You know, the essential building blocks for absolutely everything, from a tiny microbe all the way up to us. Okay, let's dive in. Here's our game plan. First, we're going to look at what makes carbon so special. We'll uncover its unique superpowers. Then, we'll get into how molecules get their identities, and this is really cool, how the same exact pieces can build totally different things. After that, we'll see these molecules in action and finally tie it all together to see why this stuff really, truly matters. So let's start with the star of the show. The best way to think about carbon is like it's the universe's most versatile Lego brick. Seriously, it's the one piece you can use to build just about anything, and it all comes down to one simple but incredibly powerful number. And that magic number is 4. This is carbon's superpower. It means it has this amazing ability to form 4 strong, really stable connections, what we call covalent bonds, with other atoms. This is the absolute key to its incredible potential to build just about anything. So because it can form these 4 bonds, carbon can do some amazing things. It can link up with itself over and over to create these long, sturdy chains, or even loop around to form stable rings. And it's not picky. It plays really well with others. It'll happily bond with hydrogen, oxygen, nitrogen, you name it. This incredible versatility is exactly why there are millions and millions of different organic compounds out there. All right, so now that we know carbon is the ultimate building block, let's get into the specifics. What are the superpowers that let these blocks actually snap together to create the insanely complex structures of life? Superpower number 1 is covalent bonding. You can just think of this as the fundamental glue. Instead of one atom stealing electrons from another, they share them. And this sharing creates a really strong and stable connection. So in a simple molecule like methane, you've got one carbon atom sharing its electrons with 4 hydrogen atoms, making this perfect, stable little unit. Now this next superpower, this is where carbon really starts to show off. It's a special ability called catenation. And all that means is that carbon is fantastic at linking up with other carbon atoms, forming those super long chains and intricate rings that become the backbones for, well, everything from plastics to proteins. Okay, so if these carbon chains are the backbone, the basic skeleton, what is it that gives a molecule its specific personality, its function? Well, it's all about the special pieces you attach to that skeleton. Chemists call them functional groups. Now, what's really interesting here is how these tiny little attachments can completely change a molecule's entire behavior. So for example, you stick an OH group onto a carbon chain, and boom, it's now an alcohol. You swap that out for a COOH group, and now you've got an acid, like the acetic acid that makes vinegar sour. These functional groups are basically identity tags that tell a molecule exactly how it's going to act and react. So here's a fun thought experiment. What if you have the exact same set of Lego bricks, but you just assemble them in a different order? Well, you get a completely different model, right? In chemistry, we have a name for that fascinating idea. It's called isomerism. And this slide just illustrates that point perfectly. Look at these 2 molecules, butane and isobutane. They have the exact same chemical formula. 4 carbons, 10 hydrogens. That's it. But just by arranging those atoms differently, one in a straight line and the other with a branch, you get 2 totally distinct substances with different properties, like their boiling points. This is absolutely critical for things like refining gasoline. In organic chemistry, it turns out structure is everything. So we have our building blocks, we have our specialty pieces, and we know we can arrange them in different ways. But how do we actually build these things or change them or break them down? Well, that's where chemical reactions come in. They're basically the instruction manual for molecular construction. First up, you've got an addition reaction. Imagine you have a spot on your molecule with a double bond. You can think of it like an open connection port just waiting for something. This reaction lets you literally snap on new atoms right across that bond, just like we see here when ethane grabs a hydrogen molecule to become ethane.
Next up, substitution. And this one is thankfully pretty intuitive. It is exactly what it sounds like. You just swap one atom or a whole functional group for another one. It's kind of like taking a red Lego brick off your creation and clicking a blue one on in its place. You've fundamentally changed it.
And finally, we've got the elimination reaction. This is basically the reverse of addition. So instead of snapping pieces on, you're popping them off. By removing atoms from carbons that are right next to each other, a new double bond forms between them. This is a really important way to create new connection points for other reactions down the line. Okay, we've covered the rules, the pieces, and the basic moves. So, let's get to the crucial point. Why should any of this actually matter to you? And the answer is pretty simple. Because organic chemistry is quite literally everywhere. Think about it. The drugs that heal us, they work because they have specific functional groups designed to interact with our bodies. The food we eat, that's all built on long carbon chains of carbs, proteins, and fats. The fuels that power our cars, those are just hydrocarbons, and their different isomer structures determine how well they work. I mean, from the plastic in your phone to the soap you used this morning, it all comes back to the chemistry of carbon. And that really gets to the heart of it. While it might seem super intimidating at first, organic chemistry isn't really about memorizing a million different facts. It's about recognizing patterns, about learning a logical language. And once you start to grasp the rules, you realize the whole thing is just a fascinating, incredible puzzle, just waiting for you to solve it. And the pieces of that puzzle, well, they build our entire world.